Let's go over the question for functional programming that I did. So in this question, I think I did relatively well because I sort of did a similar question in the past. But I think the major thing that I was missing was just I kind of forgot the strictness, what it meant. And also I kind of forgot like how to write up a proof like kind of properly, formally. Because like I lost several marks in the later part E and part G, like the proof questions, because I didn't do it properly. Okay, so let's go over what it is. In this question, we have the predefined function take is of type int, and then next is a list of A's, and the output's a list of A's. Returns a prefix of a given length from a list, or the whole list if it is shorter. Write out the equation that could serve as a definition of take. Is take function defined by these equations strict in its number argument? Is it strict in its list argument? Explain your answers. Okay, so this is like the thing I did for my correction. So I know that this is a type, right? So then if it was 0, then I would output an empty list because I'm not taking anything, right? And on the second thing, if I was to do, let me check. Yeah, I'm recording. If I am doing the second thing, then I know that, okay, if it's I'm taking in things from an empty thing, then I would have an empty thing as well, right? Because there's nothing for me to take. And then the third thing is that if I have something that's proper like this, then I would just take the x of the first element and then I have n minus 1 elements to take from the remainder of that, right? So this is just the classic pattern matching. And then this is sequential from left to right, right? Because and top to bottom. And then we're basically forced to evaluate the first argument because in the first statement it takes 0 of x's. So it means that we have to compare the first number element to 0, which means we evaluate it. So then that's strict. Whereas the second argument is not strict because if it was anything and then the first one was 0, we would have gotten it to a this, which would mean that it was not evaluated, right? So yeah, first element is strict, list elements not. Moving on to part B. The predefined function zip width of this type combines pairs of corresponding elements from two lists, discards a tail of either list argument which is longer than the other. Write out the function of this, what is this argument in the strict, explain your answer. Okay, so zip width, we can write it as this form, where we just pattern match it, right? If we have a first element from this and an element from that, we would just zip up the elements of this by applying the function f to x and y, and then we have the remainder part with x's and y's, right? Continue on. And if it's not possible, then we would just return an empty list, which would just kind of get what we need. So we know that inside here, we have to evaluate the first one, right? Because it's sequential. So we're going to evaluate X, match it, pattern match it to this, so we would evaluate. But if that was false, then we would have jumped right here. But here we don't evaluate anything, so the second argument is not evaluated, so it's not strict. So yeah, it's the same as before. Part C, what does it mean for two functions f of A to B and g of C to D are equal? So for two functions to be equal, the types have to be equal and the outputs have to be equal for the same inputs, right? So yeah, pretty straightforward. Types equal, so A equals C, B equals D. And then for all x that are of type A, f of x equals g of x. So yeah, pretty straightforward, I'd say. For part D, what exactly must be checked to prove induction on x's that f(x)s equals g(x)s for all list x's? Okay, so this is for all lists, so we definitely have to consider four cases, right? There's 4 points. So we have the bottom case, so f bottom has equal to g bottom. The empty list case, so our base case is equal to f of this is equal to g of the empty. And then the inductive step, right? F of x is equals g of x's. Then we want to show that f of x x's is equal to g of x x's, right? Yeah, inductive step. And finally, to show that for infinite lists that is true, we want to show that the claim is chain complete, which follows from the definability of F and G, which would follow from Haskell definability. So yeah, these are the four parts. And then the next part is prove that with this equation is true. So this means that we're going to have to do what we just said, the condition, four conditions we have in part D, and apply it to this equation, right? To solve this, let's just write this out. They did it in point free form, so I just rather like to write out my arguments, x's and y's in full, so it's nicer. So yeah, we're gonna do proof by induction or excess. And then here I wrote LHS is short for left-hand side and RHS for our right. For the case, we're gonna start off with bottom. If it's bottom, the left-hand side would be zip with f of this of bottom. If we're zipping with bottom, because we know the first argument is strict, hence, yeah, it's gonna be bottom. Inside here, we have the map of this. The map would return is strict, so it's going to be bottom, and we're also with the first argument's bottom, so hence it's bottom. So the left-hand side is equal to right-hand side. For the second case, when x is equal to empty list, we have the left-hand side is equal to zip width f of empty list, right? And then by definition of zip width, if it's empty, then it's going to be empty. And then the right-hand side map of an empty list is just empty list, so then the same thing would apply. So it's also empty. So the left is equal to the right. For our inductive step, our inductive hypothesis is that this equation holds, right? So we want to show that for the next one it holds. So for x of x's, y's of y's, we have that. To be honest, I don't even need to write the y's of y's. I could just keep as y's for simplicity. But essentially what I do is I write this out and then I kind of move this y term. Yeah, I do need to keep it so that I can kind of work with here because I do have to extract one element out. So if it would be f of h of x, y would be and then cons zip width f of h of x's, y's. So this is by definition of zip width. So I just move the first element implied and zip it together. And the next what I do is I see that the right hand side is essentially the like the previous part, right? So I can apply the inductive hypothesis and I would just have the right hand side of what I had. And the next what I know is that, okay, I have this part, right? So I want to put this front part back into the equation. If I want to put it back, I have this is the first element, right? HX cons map of whatever, and then Y cons Ys. So that would be my step. And I see that, okay, h of x, map of h of x. This is just the definition of map reversed, right? So we're going to put this back in here. Map of, I'm missing an h here. It should have been map of h of x's. So yeah, and then it would be the right-hand side. And then lastly, we finish off the proof by saying by chain completeness of equations, result is true for all list x's. Okay, moving on to part F. The take lemma is a statement that two lists, x's and y's, whether partial or not, whether infinite or not, are equal if only if take n x's is equal to take n y's for all natural numbers n. So this is the idea that, okay, yeah, if the first part is the same, then the second part is the same, and the third part is the same, all the way up to the end part is the same, then it's the same. That's pretty straightforward. For part F, we're asked to find one way of proving this is taken as is you use this induction on the natural number n. In order to do this, what is exactly is it necessary to prove for particular x's and y's? For part F, basically, there are two cases, right? For induction, we want to show that there's the base case that works, and then the next part is the inductive step that works, right? For the base case, we actually don't need to show it because take zero x's is if you're taking nothing from something, it's not independent. It's independent from what the list is, and this is the same with y's, right? So we don't need to prove this point. It's already true by default. So then the next step we do is kind of just show the inductive stuff. So then take n x's is equal to take n y's. If that is true, then take n plus 1 x's is equal to take n plus 1 y's, right? That's the part we want to show, the inductive stuff. Okay. Um, for part G, the predefined function iterate of this type is defined by this equation, right? This thing over here. Use the take lemma to prove carefully that if HG equals GH, then map of this is this. So this is our assumption. And then this was the definition of iterate, and then we want to show this. So for this part, we just kind of work from what we know, right? Yeah, we're trying to prove by the take lemma that this is true, right? So our induction hypothesis, and the emphasis here is for all y because you can have 1, 2, 3, all the way up to n. So for all of them, it should be true that take n map of h of iterate gy is equal to take n iterate g of h of here should have been also y, I think. So we want to show that it's true for n plus 1. So then on the left hand, because we already have the base case earlier from part um, F that like basically we don't need to show for 0 the base case because it's true by default. Then we're just left with the inductive step, right? So we're going to start with the left-hand side. Left-hand side, we first apply the definition of iterate. So we're just going to do one iteration, right? This was the original statement. If we apply one iteration, it would be g of x, right? And then we would have the x in front because that would be the first element. And then this would be the remainder element, right? And then next what we do is take. So we're just going to, I'm not there yet. So first is map. I have to first extract it out, right? So I'm going to just apply h of x to h to x so that I get h of x. And then I have the remainder of the map. So then next by take, I can just move h of x outside here. And I would be taking the end of this remainder thing, right? And then I see that, okay, I'm finally back to my induction hypothesis form, except with y equal to g of x. So hence, I would just apply, and I would change the left-hand side now to the right-hand side, except with g of x as my y. And then I know that by composition and also by g of h is equal to h of g, then I can rearrange this to be iterate of g of h of x. So that I change it slightly from this form. Then I can apply my definition of take to combine the h of x back to this equation. So it would be n now goes to n plus 1, and then h of x of iterate this thing. So then I just put this back into the definition of iterate. I would just have iterate of g of h of x. So that I get my right-hand side. So I'm done my proof. And then finally, to finish this question off, we're asked to prove that zip with this equation f of g of iterate g is equal to zip with f of iterate gg. So for this, what we do is essentially because it's a 2-mark question, we know we're not going to do a full induction proof. We're just going to use what we have from before, right? So this was the equation we have. This looks awfully similar to the form, the left-hand side to the form in E. So we're just going to replace that thing with the um, using property E. We're going to get this, right? Um, and then next we're just going to use property G. And now we're going to get this of what we need. So it's pretty straightforward. I'd say it's like the form is quite matched up exactly, so you know what to apply. I think for this question, I can also go over what I did, like when I first tried to solve this question. These were the work I did. For the part A, part B, like the functions were correct, but the strictness kind of argument is wrong. For part C, it's correct. For part D, um, yeah, I think overall it is correct, but it's a bit iffy with the um, kind of chain completeness part of the argument. And then for part E, um, I think the main kind of induction part is all right, but yeah, the could be a bit more clear. And then also one other thing is kind of weird to just do left hand side and right hand side. It's ideally just better just to go left hand side all the way to right hand side. And then for part F, Yeah, this one was not done very well. I realized that zero is kind of true by default. So I was thinking, okay, maybe I need to check the base case instead for one. But instead what I know is okay, that's true by default, so I don't even need to do this. So that's why that part is kind of iffy. Inductive step, that's true, yeah. And then for part G, I think it's done a little not too formally because yeah, I didn't like the take llama. I know that I had the right idea, but it was not done formally enough with the every step rigorously. It was just kind of like, okay, I'm saying that the previous n minus one parts, which is not the best, right? And then the end term is this. So like it's the right idea, it's the right things, but just not done formally enough for part G. For part H, there's not much to say about part H. It's just applying the previous part. So part H was done okay. So overall, I'd say like yeah, definitely the strictness part and just the formal part for G was kind of where I was lacking in this question. But I think overall it was relatively doable.